Okay, we're recording now. We're talking about rotational motion today. A couple of concepts that you're probably aware of already. The first is tangential speed, and the second is rotational speed. The rotational speed is how fast you rotate something, right? So if you have a top and you spin it slowly, it has a slow rotational speed. If you spin it really fast, it has a fast rotational speed. Rotational speed is expressed in revolutions per second or revolutions per minute, or it can be measured in degrees per second or degrees per minute. Here it's just talking about revolutions or rotation. So if you rotate something with a certain degrees or rotations per second or per minute, that is its rotational speed. Now when the object is rotating, what happens is that the periphery of the object has a certain linear speed. Did you have a question, or I thought I saw you shake your head. Okay.
Me?
No, I think you. Nope. Okay, cool. Samantha, right?
Yeah.
And Wendy?
Yeah.
Okay, perfect. And Lonzo? Okay, excellent. Okay, so tangential speed is the linear speed along the curved path as in circular motion. So if we're driving in a circle, whatever your speed is tangential to the circle is your linear tangential speed. Okay, so here is a CD, for instance, that's rotating at a certain fixed rotational speed, which is a certain number of revolutions per minute. And what happens is, if you had a position, a point over here, let's say in 1 second this point travels this distance, a point that is further away from the center travels a greater distance in that same 1 second. Both of these are traveling at the same rotational speed. Are they traveling at the same linear tangential speed?
No.
Nope, you're right. Because what happens is this object travels a greater distance in the same time. So its speed is greater than here. So this is making the point. So here's your CD player or your record player or whatever, and here's the ladybug. If the ladybug were at the very center so that the radius is 0, the ladybug would just be spinning around but would not have a tangential speed as such. If the ladybug were to walk halfway from here to the radius, to the halfway point, she'd be traveling at a certain speed. If she were to move to the very edge, what happens is she would be traveling twice as fast as over here. Now this is something that's intuitively evident to us. This can be captured in this formula. V for velocity or speed, tangential to the circle, will be the radius r from this distance from the center to that point, center to this point, multiplied by omega. This letter is the Greek letter omega, the little lowercase letter omega, and that stands for the rotational speed in either rotations per unit time, rotations per minute or rotations per second, or alternatively in degrees or radians per second. So velocity equals radius multiplied by angular velocity. Okay, introducing another term, rotational inertia. Rotational inertia, we've seen inertia in the past, right? Regular linear, if you will, inertia is the tendency of an object to stay stationary if it was stationary to begin with, or to keep moving if it was moving to begin with. So if an object is moving, to stop it, what would you have to do?
Apply a force.
Apply a force, right? If you do not apply a force, it wouldn't stop. It would just keep going on indefinitely, right? Similarly, rotational inertia is the tendency of an object that's rotating to keep rotating. If you don't have any friction, it will just keep rotating indefinitely. That movie Inception, was it? Remember the yes, they spun it, and if it was in the real world, if I recall correctly, it would slow down and come to a stop. However, if you were in your fantasy world, then it just keep going, right? So that was whatever, I forget what they call it, talisman or something. It is a way of your telling whether you were in the real world or in the fantasy world, right? So that is an example of rotational inertia. If there were no friction at all, the top in real life, once you spun it, would just keep on spinning indefinitely. It would never stop, in principle, right? But if there is any friction, then what would happen is that there's a force, a torque, in the opposite direction of the direction of rotation, and this would slow the top down and it comes to a stop. So that's what rotational inertia is about, the tendency to keep rotating if you were rotating. So If you had barbells, for instance, so you got the inner rod and then you got the two weights. If you were to put the weights very close to your hand, then what happens is it's easy to rotate. However, if you move this further away, it's harder to rotate. Best thing is to try this, and you will find that that is indeed the case. And an application of this is a circus. Here's a person that's walking a tightrope. Is it easier for the person to walk the tightrope when this bar or rod or pole that the person is holding, when it's long or when it's short? Long, right? Does anyone wish to disagree? Nope. Now, you're right. When it's long, what happens is it's easier to balance than when it's short. If you were to try to do the tightrope with a rod this small, it wouldn't help you at all. However, if you have one that's, I don't know, maybe as long as this, the fluorescent lights, or maybe a little shorter than that, that would actually help you to balance. What is happening is that this object has rotational inertia. Let's say you're going to start falling. You start falling off, right? So you have to rotate about the tightrope. This whole rod is going to have to rotate for you to fall off. If you're going to fall off in this direction, the rod has to rotate, right? But the rod has rotational inertia. This rotational inertia is greater if the rod is longer. And because it has a greater rotational inertia, what happens is holding onto the long rod actually helps stabilize you, because when you start going this way, the rod resists your rotation and helps you get back stable. Or if you go this way, it resists the motion and helps you be. So you know what happens during a circus? If the person lets go of the rod, what happens? The rod falls. Then what happens? They then fall, right? And instinctively, what do I do? What do they do? Like, let's say that you were walking upon like a narrow wall. What do you do with your arms when you're trying to balance? Stick them out, right? So what happens when you you put your arms out? You are basically creating a situation like this. So your arms are going to resist the rotation that's associated with your falling off, and so it makes you more stable. So these are things that you do intuitively without even realizing why you do it. In physics, we're just commenting on what you do intuitively and say, hey, here's the law, right? Here's the reason why it works. Think of this, 2 meter sticks, right? Here's one and here's another. There's a bunch of dough, Play-Doh or whatever, that's a blob that's fixed on the very end of this meter stick. Both of these meter sticks are held against the edge of the wall. It's like if I were to take one of these sticks and hold it like this, right? And I have another one exactly the same as this, except it has a weight at the top, Play-Doh. Which of these sticks is going to hit the ground first as it rotates about this edge? See, I'm going to let go. See what happened? Now if I had another stick like this that had a blob, a weight on the end, Play-Doh, would they both hit the ground at the same time? No. Nope. Which would hit the ground first? Okay, how many of you go with the one with the Play-Doh, with the weight? Okay, 1, 2, 3, 4, 5, 6. And how many of you go with the unplay-dohed, the one without the Play-Doh? 1, 2, 3. Okay, how many of you did not vote? How many of you who did not vote are not going to admit to not having voted? How many of you are in a coma? How many of you are awake?
Awake?
Yes. Okay, great. Okay, how many of you who did not vote? Yes. Okay. So, do you want me to give you the answer? Do you want to research it and find out?
I want to know what that is.
You want to know what the answer is? You want me to give it to you? Okay. Yes. According to physics, what happens is the one that does not have the Play-Doh is going to hit the ground first. Intuitively, I would have thought the other way, right? I would have thought that the Play-Doh on the top makes the top of this heavier, right? It's heavier here, so there's more force pulling down.
Yeah, because it's not like arms hanging out that the rotations.
It's actually similar to the arm situation.
What, the Play-Doh?
Yes. What happens is, think of this, like here's my center of rotation, right? If I'm going to fall off of something, like I'm on a wall. If I stick my arm out, what am I doing? I am moving some of my mass out to the ends, further away from the axis of rotation. Same thing here. Here's the axis of rotation. If I were to move mass to the end, it's the same thing as if I were to extend my arms. So what happens is this becomes more stable than this. This mass here resists the torque, and we'll talk about torque in a minute, that is causing this to rotate.
Even when it's I can see that if they were like standing straight up, but I guess I'm thinking if they're like diagonal already, I would think that it wouldn't matter. But
Yeah, well, what physics, it's kind of like saying if I were on this, like on a wall or something, and if I'm tilted a bit, am I more likely to fall if I'm like this or if I'm like this, right? This way, I'm not able to balance, but if I had this out, then it gives me a chance to compensate it. So in a sense, right? But basically what's happening is it's rotational inertia. We're rotating about this axis, this fulcrum, if you will. The mass is greater out here, and so what happens is there's a greater rotational inertia, greater resistance to the rotation. So this is harder to rotate than this one.
They're already tilting, so they're going to fall.
That's true. Both of them are going to fall.
So it seems like the one that would be heavier would fall.
That's what we would think intuitively. But rotational inertia says our intuition is incorrect, right? I know. Okay, summary of terms. Moving on to the next concept, torque. Torque is the product of a force and the lever arm. So torque is lever arm multiplied by force. It will make sense when we look at an example of this. Then introducing equilibrium. You've already seen equilibrium for linear motion. In the case of linear motion, linear forces and so on, equilibrium is where the sum of all the forces in the object is 0, right? So the fact that this meter stick is not leaping about, staying stationary, is an indication that the two major forces on it, one is its weight, the earth pulling it down, the other is the normal force on the table. These two exactly cancel each other, so this object is in equilibrium. So you could call this, if you will, linear equilibrium, right? Because this is not moving in a linear direction. In this case, we're talking about rotational equilibrium. For total equilibrium, which includes linear equilibrium as well as rotational equilibrium, there has to be no net force and no net torque. So torque is a tendency to rotate this, right? So if there is no twisting force, if you will, no torque, then what happens is the object stays stationary instead of starting to rotate. So here are some illustrations of torque. If you had a meter stick and you're holding it at the very end and then you apply a weight here, is it going to be harder for you to keep this from rotating when you put the weight close to your hand or far away from your hand? Yep. Up. Is it going to be harder to keep it from rotating?
keep it closer.
Okay, middle compared to?
Because on the end it can be harder.
Yep. So intuitively you're correct. If you move it away, if you move the weight away to the end, it's harder. And the reason why that's the case is the torque is greater. The same weight, so it's the same force, multiplied by the lever arm, right? So this lever arm is greater, and so the torque is greater for a given force. If I take the same force and apply it in the center, the torque is smaller. So it's easier for me to compensate and keep it. Same application here, or similar application. Here's a seesaw. There's, let's say you take your niece or your nephew to the playground, and the niece or the nephew is lighter than you are. Do you place the niece, or let's say that's your nephew. Do you place, okay, actually that won't work. Here's the niece, right? Do you place the niece closer to the to the edge, or closer to the fulcrum of the seesaw to balance you? Further out, right? Anyone disagree? The person who's lighter sits further out in order to compensate for the torque created by the heavier person. So you see this in this case, where the lever arm from here to the boy who is 500 newtons, that is his weight, 500 newtons multiplied by 1.5 meters. Now to balance this, you'd have to take the 250 newton girl, so she is half the weight of this guy, and multiply by 3 meters. So you can see the lever arm has become bigger, right? So greater lever arm. The torque, we said, was the lever arm multiplied by the force. So 3 multiplied by 250 gives me 750. And that torque is rotating this, trying to rotate the seesaw in this direction, in a counterclockwise direction. His torque is trying to rotate it in a clockwise direction, in the opposite direction. And let's look at the numbers. 500 multiplied by 1.5 is what? 750. So multiplying the two of these gives you the same number as the two of these, except that one, about the fulcrum, one is trying to rotate it clockwise, the other is trying to rotate it counterclockwise. They're exactly the same, and so they exactly balance out. So the key thing to notice, if the boy is heavier, he needs to be sitting closer, the lever arm is shorter compared to the girl who's further up. You see similar application, like if you have a flat and you're trying to undo the lug nuts on your car, and here's your wrench. Is it easier to undo the lug nuts when your arm is holding the wrench closer to the nut or further away from the nut? Further away. Classic example where you need a certain torque to undo the nut. You increase the lever arm, which means you need a lighter force. So it's easier for you to do this, right? And the point that this is making, yeah, so you can get even more torque by taking don't do this because it can be dangerous, like a copper pipe or something, and sticking it over the wrench, so extending the length of the pipe, right, up the wrench, and so you're increasing the lever arm, and then you pull up, or alternatively you just get a wrench that has a longer arm, and that'll be easier. This is making the point that the torque considers the force that's perpendicular to the lever arm. Here's the lever arm, the force should be at 90 degrees to have the greatest impact. If the forces are off at an angle, what you'd have to do is you have to calculate the component of the force that's perpendicular to the lever arm and use that force multiplied by the lever arm to get the torque. Okay, introducing the concept of center of mass and center of gravity. Now the center of mass is the average position of the mass of an object. So don't do this experiment at home or elsewhere, but if you had a baseball bat and if you were to put the baseball bat here, in principle you should be able to balance yourself stiff as a board on the baseball bat. So it's a matter of where would you place the baseball bat. If you're able to hold yourself totally stiff and you lie down on the bat, I'm not going to do this, right? So where would you place the bat? You'd want to place it at a position that, whatever the position you place it at that works, is the center of mass. So typically, since we are bilaterally symmetric, we have approximately a mirror plane through our middle like this. What happens is our center of mass will be somewhere down this middle line, right? And then if you look at the distribution of mass above versus below, you'd want a section somewhere here. So for most people, the center of mass will be somewhere between your solar plexus, sternum, and your belly button, right? So, right, if you're an apple versus a pear, it'll shift up and down, right? Shape. Was it a question?
Is it kind of the same?
By the way, extra credit to you for the previous question and extra credit to you for this question.
Thank you. Is it the same principle as the teeter-totter thing? Because you... Is it? Because I'm just thinking of the way that it looks with them.
Yes.
Okay.
Yes. So let's say, like if you're trying to balance yourself on the baseball bat,
Right.
what happens is it's like you are a teeter-totter or a seesaw along the x direction and also the y direction.
Okay.
So you have to place this at a position that, so that the weight below this position is equal to the weight above, and also in this plane so that the weight to the left is equal to the weight to the right.
Okay.
So that position for any object would be its center of mass, which is the top line, right? Center of gravity is typically the same as the center of mass. It's typically the same as the center of mass, but this is talking about the effective action of gravity. So center of mass doesn't say anything about force. It just says the body behaves as if its mass is all concentrated in that point. Center of gravity says gravity is going to act on this object as if all of the mass of the object is in this position. Yeah? So typically, to a first approximation for the level of this course, the center of gravity is equal to the center of mass. Do you want me to give you a real life reason why that's not the case? Do you want to think about it? Okay, think about it, and extra credit assignment, come up with an example. Under what situation would the center of gravity of an object not be equal to its center of mass? Under what kind of a situation?
Something like the banana thing, where it can be outside of an object, where its mass would be obviously inside of the object, but the gravity would be outside of it. It is true that the center of mass. It's true that the center of mass of an object can be outside the object, because, like, if you look at a crescent,
right? Like the banana, then what happens is the center of mass will be somewhere in the area that's subtended, not actually in the banana itself. But if you're trying to apply that to this, you'll have to come up with the reasoning, right? So that's an extra credit, one of those shy extra credit assignment to find out. And if you don't get the answer, catch me, ask me next week and I'll tell you, right? Okay.
Send that to your email, or we put it into the extra credit box?
You put it into the extra credit box because it's a simple answer, right? Yeah. Okay, so application, center of gravity, the Leaning Tower of Pisa, right? You all know that the Leaning Tower of Pisa, when they first built it, was vertical, right? And what happened is, like, due to moisture in the soil and that kind of stuff, the soil started settling more on one side than the other side, and so the tower started leaning. And then, if I recall correctly, they actually tried to build some supports. They tried to change the orientation at the top and stuff like that to kind of counterbalance this. So what happens is the center of gravity of this entire structure is somewhere here, and if you project it down, it falls inside the bottom of this. Now, if the center of gravity were to move outside of this, the tower would fall over. So here's an illustration, right? Where if you look at your feet, when you stand normally, what happens is your feet create a trapezoid, like a squished rectangle. And your center of mass is projected downwards somewhere inside that trapezoid, right? That's what keeps us from falling over. Sorry?
Is that where you get your balance, right?
Yes. Now what happens is, like when we walk, we are moving our center of mass outside of the rectangle actually. You move it out, then you start falling. Then you stick your leg out and you stop. So walking is actually a series of falls. You fall and catch yourself, fall and catch yourself, fall and catch yourself, right? And of course, if you're a toddler or whatever, you fall and don't catch yourself, right? So here's an experiment. If you're going to do this at home, make sure there's plenty of pillows, right? What you're going to do is, normally, if you were to do whatever this is, like you're going to touch your toes, right? When you bend over, here's your center of gravity, right? Let's say slightly above your belly button or in the vicinity of your belly button. What happens is, as you bend over, notice that your behind moves backwards as your front comes forward. So what happens is, the center of mass or center of gravity stays above that trapezoid. Now, when you try this exercise, we just naturally do this, like our behind moves backwards when you try to bend over. You can prevent that by standing straight up against a wall. If you stand straight up against a wall, now you bend over. So now what you're doing is you're preventing your bottom from moving backwards. So your bottom is directly above the trapezoid. What this does is, now your solar plexus, your belly button, whatever, are shifted outwards out of that trapezoid that's created by your feet. What happens to you?
That big old head makes you fall.
Yep, you fall over, right? So if you're going to do this experiment, make sure there are pillows and so on, and you're welcome to videotape it and put it on YouTube, and I'll give you extra credit, right? And double the extra credit if you're able to do it without falling over. If you can do that without falling over, right? That actually makes me think of this. I haven't seen Michael Jackson actually do this, but I had heard that he had actually filed a patent for a method by which he would have certain, I forget how it was, like spikes in his shoes or something like that, and at certain places on the stage, he would have these sockets where he could go and, of course the audience doesn't know, right? He could go and stick the spike in his shoe into a socket, and then he could lean over in ways that would, as part of his act, his dance and so on, he would lean over so that his center mass is substantially outside of the trapezoid of his feet. And normally normally if somebody were to do that, you'd fall over. So to the audience, it's like, wow, how did he do that, right? So now I've never seen him do this. I haven't seen enough of his music videos to see him actually do this. But if you find one, extra credit if you can send me a link, if it's a YouTube video or something that I can show in a class at some stage, right? Okay, so that is an illustration of this, or this is an illustration of that. Okay, centrifugal force. Introducing centrifugal force and centripetal force. Now, let's say that you are on a merry-go-round. What's the other word for a merry-go-round? Carousel. Thank you. Extra credit to you. So let's say, because that's the more commonly used word here, right?
No, merry-go-round.
Oh, merry-go-round is more commonly used? Okay, then we shall stick with merry-go-round. So here's the thing, because I grew up with Commonwealth English, kind of like the British English and that kind of stuff. So sometimes what happens is the words that I use may be a different word that's not as commonly used in the US. And so if I say something and like I get all these blank stares, then I realize I need to go back and replace a word. So merry-go-round. So we are on a merry-go-round. We're traveling in a circle, right? And let's say that you're on here. This is the center of the merry-go-round, and you're on a little horsey, right? You're on a horsey. What happens to you as the merry-go-round speeds up? Do you get a force that is trying to push you towards the center? Nope. To outwards, right? So the force tries to push you outwards. That force is called the centrifugal force, right? That's the top force. It's the force that makes it look as if we're going to be, and it's true, if we don't hold on to the little horsey, they'll get thrown off, right? Here's at least one person who's actually been on a horsey on a merry-go-round, which is awesome. Extra credit to you.
Thanks.
Right? So now what happens is, here's Samantha on the horsey, right? On the merry-go-round. And the horsey, the centrifugal force is trying to throw her off. What keeps her on?
Gravity.
But gravity is pulling downwards. The centrifugal force is trying to kick her in that direction. What?
Inertia.
Okay, inertia is actually, that's the next step is to realize that centrifugal force is due to inertia. So inertia is actually helping the centrifugal force. It's inertia that's trying to throw her off. So what is it that's keeping her on? What? What is she doing to stay on? She's holding on to the horsey, right? Like holding on to the neck for dear life, or holding on with her legs, right? Whichever you could. So if you were to hold on with your arms around the neck of the horse, then what happens is let's say that she is being thrown in this direction, right? By centrifugal force. So she will apply a force, her arm holding on to the horse's neck, right? This arm would basically apply a force in that direction, counteracting the centrifugal force. That force is the centripetal force, the second force. So the centripetal force is what is holding you on. It's pushing you towards the center of the rotational motion. The centrifugal force is actually not a real force, it's an imaginary force. It's an apparent force, or an imaginary force. Really, it is not an extra force, it's just her inertia, right? The fact that your inertia tries to keep you going in a straight line. So as the merry-go-round is turning, her body says, no, I want to go in a straight line. And she experiences it like force is trying to throw her off. And if she does not hold on, that inertia will throw her off. Right? Clear? So is centripetal force a real force or an imaginary force?
Real force.
It's a real force, right? Because you're holding on, you're applying a force. Or it's friction, right? Like you hold on with your legs or whatever, it's friction between your legs and the horse. And centrifugal force, is that a real force or an imaginary force? It's an imaginary force. Or an apparent force.
Or what?
Apparent, like here, here. It is an apparent force or an imaginary force. This word here. Okay, so here is an illustration of this. If you were to take a little tin can, tie a couple of strings to